Okay, I got another question. This one is from chapter 35, number 35. Okay. And so this one says, consider a common mirage formed by superheated air immediately above the roadway. So this problem can be challenging just to understand the physical picture of it. And so imagine this is a road here, and so I've got this car. And the driver is in the car looking out. And if you've ever been on a long straight road, and particularly a desert road, as you look out, you'll see what looks like a mirage, what looks like water out here. And what actually is happening is the air is getting really hot, and that's why the problem uses this word superheated air, right above the surface of the road. So the sunshine is up here, and particularly again if it's a hot desert road where it's both straight and hot, and then the black asphalt, you'll get this so hot that this spacing between the molecules is much bigger than the spacing of the molecules that are maybe a couple of feet up above the road. And so if we look at the index of refraction, which remember comes from saying this is the speed of light in that medium, the reason excuse me, the reason it slows down is because it interacts with the air. And so what happens is the index can be a little bit lower in hot air than cold air. And then we get into this part of the chapter, if you remember, total internal reflection. And that is that if you had light coming to this interface between the hot and the cold, because the hot has a slightly lower index, it may bend it upward, something like that. And remember that total internal reflection only occurs when you go from one index into another here. And so that's part of this discussion here. What is that index here? And so if we take then, depending on what we look up here, but why don't we say then that we know the lowest the index can ever get is, well, the lowest it can get is lowest is 1. And when we look up on the table, we see that they list the index for air to be 1.0003. So I'll take that as being the cool air, not the hot air, since the table lists it as air. And I think it even says 20 degrees. Maybe I should go back and look here. I'm going to take a second and do that. Where does it give the index? Yeah, it says air, gases. Actually, this says at 0 degrees Celsius. Actually, then they say 0.293. Anyways, that's just a long way of saying I'm going to take the value in the book. And so I would expect this hot air to be a little bit smaller, but not less than 1. And, of course, then the reason the driver is kind of interpreting this as water over here is this is probably light that is coming from the blue sky. And so the sunlight goes through the air. The blue light scatters more. That's why the sky looks blue. So unless you're looking directly at the sun, if you're looking someplace at the sky here, as the light goes through, you'll see it look blue because the blue scatters a little bit better. That's actually a good discussion of chapter 38. But then the blue light here coming towards the hot air then goes under a total internal reflection, and then goes to the driver. And of course, we also know that hot air rises, and so this index here will kind of fluctuate, kind of change, and it's this fluctuation then that will make this beam kind of dance around a little bit. And so what the driver will see, what will look like an appearance to them, is kind of this blue off on the road there, and it's kind of dancing or shimmering, and that would kind of give the interpretation that there's water on the road because it's blue and it's kind of dancing. In fact, you can see the same thing with the stars when you look at the starlight at night. As it goes through the atmosphere, there's different temperature zones, and the turbulence in the air kind of makes the starlight twinkle. And so starlight twinkles. The moon doesn't do that, or the planets don't do that, because they're actually a little bigger. And so they kind of dance around, but they don't really completely, go at an angle where they disappear and come back, so they don't twinkle. They just kind of shake a little bit, and it's so little you don't even notice it, especially if something as big as the sun, especially tonight with such a beautiful moon we have tonight. But so that's one of the ways you can see starlight. Starlight, it's a star because it's twinkling, and it's a planet like Venus. Venus is real bright now. That's not a star. Plus, it's in the zodiac and blah, 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 blah. Okay, so there's a lot of reasons why you would tell the difference between a planet and a star. But anyways, the stars twinkle, which is really kind of interesting because if you watch science fiction movies at all, sometimes they don't do that right, and you'll be watching the stars out the window of the International Space Station or some spacecraft, and they'll have the stars twinkle, and they shouldn't twinkle. That's an atmospheric effect. Anyways, I hope I didn't spend too much time here on just the general concept. But the problem itself then is actually pretty easy. It's just a total internal reflection. And so if we apply Snell's law, and so I'll just write Snell's law down here. And in Snell's law, we said that there is a special case where 1 stands for where it starts in. Okay, so it starts in this cooler air. So the index is 1.0003. And it's coming in at some angle. Let's talk about that in a moment. But if it's going to go under a total internal reflection, then this index N2 has to be smaller than this one. And it will first occur where the refracted angle is 90 degrees. Not to say the light stays at 90 degrees. This is actually goes back before we got kicked out of school. Oh, that sounds funny. Yeah, we got kicked out of school. So that's weird. Yeah, so we all got kicked out of school. But when we had to stop meeting face-to-face because of the pandemic, you might have recalled me standing in the front of the class with my arms out wide saying, okay, this side's going to hit, it's going to drag around, then it's going to go 90 degrees, but this side's still going to be in, so it's going to arch around a little bit. And so that's what we have here. So the way we find that critical angle is we set it at 90 degrees, even though it would first go 90 degrees, wouldn't stay there, it would wrap back around and then have a reflection. But you calculate it at that. So this index would be it. Now, of course, this angle could even be greater than 90 degrees, but the way the problem reads, it suggests that this is total internal reflection. So then, if I continue on here, I can put down this incident angle. And they said in the problem that the driver is then, how did they phrase it here? They say where her line of sight makes an angle of 1.2 degrees below the horizontal. So this is 1.2 degrees, which would make this over here 1.2 degrees, which would make this then 88.8 degrees, which would then make this angle 88.8. And that's the key I was looking for. This is the angle of incidence. So this is the sine of 88.8 degrees. Sine of 90 is 1. And so I can finish the calculation. And I better just check. Am I in degrees? No, I am not. Didn't think so. Okay, and so this would be, I'll start with the sine of 88.8 and then multiply it by 1.0003 and come up with 1 point quadruple zeros. 1, 2, 3, 1, 2, 3, 4, 8. Yay, and so there's the index.